Okay, so we now know what the Feynman diagrams are for our theory, and we know how to compute correlators using them. In this chapter, I want to just develop the diagrammatic notation a little bit further and show you a few standard things of working with Feynman diagrams. So the first thing that we're going to discuss is related to normalizations. So normalizations, okay? You'll see what I mean by this in a moment. So remember, we've been calculating correlators. So phi to the n, what was this given by? This was just given by taking n derivatives with respect to j of z of j, and then we said j was equal to 0. So this is how we worked out our correlation function. And what was z of j equal to? Well, z of j was some normalization. We then had an integral over phi from minus infinity to infinity d phi. We then had an e to the minus alpha over 2 phi squared minus g phi to the 4 plus j phi. And how was n set? Well, n was set as follows. We said that n times by the integral from minus infinity to infinity d phi of e to the minus alpha over 2 phi squared plus j phi. We said, well, this is something that we calculated in the free theory. So let's continue to use that result. We use that, okay? So this fixed n, so this fixed the value of the normalization n. And when I say that we're discussing normalizations, we're discussing specifically the value of n, okay? We're going to change n now. We fix the value of n, and here we were using the free theory, okay? We didn't think too much about it in the interacting case, but in the free theory, this is how we fixed it. And what did this ensure? This guaranteed that if we took z and we said j is equal to 0, and then we evaluated this at g is equal to 0, we got 1, okay? So if you wanted to write down what was the condition that we were using to fix n, this was the condition that we were using to fix n, okay? So this fixed the normalization. Good. Now, next thing I want to remind you of, just a few of the results that we calculated. So we calculated the phi squared correlation function. What was that equal to? Well, it was the sum of that diagram plus the sum of this diagram plus the sum of that diagram. And then there was also order g squared. And we worked out what each of these diagrams were. The first term was 1 over alpha. The second term was minus 3g over alpha cubed. And the third term was minus 12g over alpha cubed. And there were terms of order g squared. I'm only going to work to first order in perturbation theory, okay? And I'm just quoting things that you have calculated. So they should be in your notes. So this is 1 over alpha minus 15g over alpha cubed plus order g squared. Good. Now, I want to repeat the computation of phi squared, but now we will take z hat of j to be equal to z of j divided by z of naught. And I want you to notice something. Z hat, when j is equal to naught, well, will be z of naught over z of naught. So this is equal to 1, okay? So we have replaced this normalization with that normalization. Now we don't need to set g equal to 0 for any g. Z vanished, z is equal to 1 as soon as we set j equal to 0. Okay, let's maybe stress that. Let's maybe say for any g. And what does this correspond to? Well, you know, what we've done is very, very natural. You see, we're now going to define correlators. Phi to the n, let's call this nu, as taking n derivatives with respect to j of z hat of j. And once we've done that, we'll set j is equal to 0. Okay? And what does the new normalization imply? The new normalization implies that if we set n is equal to 0, so we calculate the expectation value of 1 in the new normalization, well, if we set n is equal to 0, we take no derivative with respect to j, so we've just got z hat evaluated at j is equal to 0, and that's 1. And this looks extremely natural. So this looks good. Why does this look good? Let me just remind you again. Remember that we said phi to the n. If you think about this, the analog of this in 3 plus 1 dimensions was the time-ordered correlator of n fields. So 1, the analog of this, would just be the overlap of the vacuum with itself, which is 1. And that's why normalizing things so that the expectation value of 1 is 1 is a good idea. It looks very natural. Good. Okay, now we also calculated z with j is equal to 0. So z with j is equal to 0, this is what we were calling the expectation value of 1, and we evaluated this. We found it was 1 minus 3g over alpha squared, and again, I will just work to first order. So if you go back and check, all of this we already did. Here I'm just using computations that we've done before. So now a natural question to ask is, what do correlators computed using z hat of j look like? Well, let's do an example. So let's calculate a 2-point correlator with the new normalization. So what is this equal to? Well, this should be 2 derivatives, z hat of j, dj2, evaluated at j is equal to 0. And we know exactly what this is. This is 1 over z of 0 to 2 derivatives, z2 of j, dj2 at j is equal to 0. And we know what each of these ingredients is. So there we've calculated the 2-point correlator. So 1 over alpha minus 15g over alpha cubed. So let's put that in. 1 over alpha minus 15g over alpha cubed times by 1 over z of 0. So let's work out what 1 over z of 0 is. So 1 over z of 0 is equal to 1 over, and let's remind ourselves, here's z of 0, good. 1 minus 3g over alpha plus order g squared. Now, remember the formula. So this is the first geometric series that you learned I'm pretty sure. And it just keeps going on. So I'm going to use that geometric series. This is 1 now plus x. So x is 3g over alpha and then plus order g squared. So that's what 1 over z of naught looks like. So let's now use that inside of phi squared nu. So we will have 1 over alpha minus 15g over alpha cubed, and then multiplied by 1 plus 3g over alpha. And of course, there are terms of order g squared that we're not tracking. So let's just multiply this. 1 over alpha times 1, that is 1 over alpha. 1 over alpha times 3g over alpha is 3g over alpha squared. Minus 15g over alpha cubed times 1 is minus 15g over alpha cubed. Sorry, this 1 over alpha times 3g over alpha squared. Okay, did I? 3g over alpha squared, good. This should be 3g over alpha cubed. And then there is order g squared. So what is this? This is 1 over alpha minus 12g over alpha cubed plus order g squared. Now, this is a really interesting result. And the reason why it's interesting is this answer that we've got with the new normalization still has a nice diagrammatic interpretation. You see, you remember that 1 over alpha is just the line, but what is this minus 12g over alpha cubed? Well, minus 12g over alpha cubed is also a diagram. It's that diagram sitting over there. So it is plus that, and then plus order g squared. So what's happened in the new normalization, in the new normalization, we don't add this diagram. So that diagram has not been added. Now, notice something. This diagram has a disconnected piece. So that sitting over there is a completely disconnected piece. It doesn't connect to anything, okay? And what it is called, whenever you have a diagram like this with the disconnected piece, so that means, remember, if we had to put our dots on for the correlator, there would be the 2 dots, and that disconnected piece does not connect to any dots. So let's put not connected to dots. That's what I mean by disconnected, okay? It's not connected to the dots in any way. A diagram like this is called a vacuum diagram. And any correlators to compute correlators with z hat of j, the only things that you need to change is you don't include any vacuum diagrams. Okay, so I've illustrated this rule to you. We're going to discuss it in a bit more detail, make sure it's all clear.